Okay, let's do a couple of examples of centripetal force and centripetal acceleration. Let's do a couple of classic examples, car examples, spinning things around on your head on a piece of string. So I am driving a car at 30 meters per second, which is slightly faster than the speed limit where I live, at 30 meters per second, and turn a corner, and go around the corner with a radius of 400 meters. So it's not a tight corner. Okay, so go around the corner, around the corner of radius of 9. What is my centripetal acceleration? Well, step 1, draw a picture. Here's my wonderful car. I'm going around the corner. Step 2 is write down what you know. So what do I know? I know V is equal to 30 meters per second. I know R is equal to 400 meters. So therefore I can work out AC, which is an equation, is equal to V squared over R, which is equal to 30 meters per second all squared over 400 meters, which I'll get a calculator. So 40 meters squared is not 30 squared is 900 divided by 400 equals 2.25 meters per second squared. So that's nearly equivalent to lateral acceleration, which is actually more than they like cars to tell. It's more than they like trucks and things to pull on an open road. Okay, so let's do part 2 of this. If my car weighs, or masses would be a better word, 1,250 kg, what is the force? The centripetal force. So let's try this. So it's going to be the same problem. So now I'm going to add in mass equals 1250 kg. So force centripetal equals mass times V squared over R, which is equal to 1250 kg times 30 meters square over 400 meters equals 2,813 newtons to 4 SF. Okay, so last question. Where does this force come from? Something must supply this force. We call it the centripetal force, but that just means the force is acting towards the center. But we apply that to, so what is the actual force? And the force is the friction from the tires on the ground. So the tires, the friction of the tires meeting the ground are what supplied this force, the centripetal force. Okay, let's just try another example then. Example 2. I like this one. I want to spin a space station to give an acceleration of 8 meters per second squared. So one of the classic sci-fi ideas is, if you want to have a bit of artificial gravity in space, spin your space station. Yep, okay, so I want to keep the velocity at 5 meters per second. So I don't want to be spinning the rim a bit more than 5 meters per second, because that'll make it hard for spaceships to dock. That's just my excuse. What is the radius? The radius of the station. Is this even possible? I don't know. So let's go find out. So we're going to make a space station. So I can stand here. That's going to spin around, and we're going to have our force centripetal. What's the acceleration going to be? Well, write down what we know. We know A centripetal equals 8 meters per second squared. We know V equals 5 meters per second. So let's go and work this out. So AC equals V squared over R. I want to find R. So we go times R times R. The reason I do this is because I want to bring the R up the top. And then I go divide by AC. Divide by AC. R is equal to V squared over AC, which is equal to 5 meters per second squared over 8 meters per second squared. So that's going to be 25 divided by 8. 3.125 meters. That's okay. Well, that answer is correct. That would not be a good space station. That would be a tiny space station. So that would be, I suppose that would actually be about the size of the inside of Skylab. So yeah, I mean, you could technically spin it.